We have a very interesting talk today in this breakout room, and it's going to be handled by Sriram Shankar. Let me give you a quick intro about Sriram. He started his career in developer tools. During this phase of his career, he built Java CC, a parser generator for Java, and founded Meta, where he built Java static analysis tools and a Java debugger. He shifted focus to search engines approximately 15 years ago. So he has a fair amount of experience. He's built search engines in use at Meta, Facebook, LinkedIn, and Uber. In this session, Sriram will be talking to us about the entire journey of a search engine, a huge value of experience. He's coming up on your screens. Over to you, Sriram.
Please. Hello. I'm ready. Can you start the presentation, please? Thank you so much, everybody. Thank you, Anuj, for the introduction. Nice to talk to all of you. I'm going to be, as Anuj said, I'm going to be talking about search engines and my history over the past 15 years, roughly, on everything I've done. And I'll try to give you a step-by-step evolution of everything that I've seen happen. Today, I'm currently at Anyscale. I've been in Anyscale for about a month. It's a company whose slogan is making distributed computing available to every developer. And it has relationship to search engines, which we might try to cover at the end of the talk if there's time, but otherwise, let's focus on the search engine part. So my background has already been covered, so I won't spend any time on this slide. And let's get started. So many years ago, when the internet just started, you used to have a search box, you used to enter text, and you hit enter. And what would happen is there would be a search engine behind the scenes that would use those query terms that you typed, and it would go and match documents that had those terms. And then it would give you the best documents that match those terms. And those best documents would be by a very simple scoring system, for example, TF-IDF. Roughly speaking, let's say you search for, let's say, t-shirt. Then you will get documents that have t-shirt in it. And documents with more t-shirts occurring more frequently would be preferred over those that occur less. If you use words in your query that occur in too many documents, those words would be deprioritized in your query. So in some sense, the importance of your term to the document is somehow evaluated through this formula like TF-IDF and other equivalent ones. And you get the best documents for your query. So this is how everything started off. And roughly around 2000, the Lucene library was released as an open source entity and has been evolving ever since, getting better and better. Lucene really supports this functionality really well. Given a bunch of terms, it will retrieve all the documents that you have indexed in its search index and give you the best documents by some simple scores like TF-IDF, or it has a bunch of them in its list. And Lucene is a library, as I mentioned. It's not a full-fledged system that you can call through an API, through a REST API. Systems like Elasticsearch and Solr have been built on top of Lucene to provide this full search capability on top of it. And I'm sure all of you have either directly worked on Elasticsearch or Solr, or use search engines that are driven by Elasticsearch or Solr behind the scenes. So what I'll do is I'll do a quick recap of how this whole system works. A search engine the index of a search engine has two pieces mainly. One is the inverted index, and the other is the forward index. The inverted index is the data structure on which the search actually is performed. You have search terms that are lists, and those lists have entries which are the documents within which those terms are present. And you form a search query, and I'll talk about it a little more on the next slide. And using that query, you find the documents that match it. And then those documents have something called a forward index, which is the metadata of those documents, using which you perform the ranking to figure out what the best matches are. So let me, the lists that we use in the inverted index each of those lists are called a postings list. I might use the word postings list going forward, so mentioning it here. Let me start with an example. Let's take a very, very simple search index with 2 documents and just focus on the words that are not blah, blah, blah. One document is Sriram at Flipkart. Think of this as maybe LinkedIn, where you have people and their companies. And another is Sriram at any scale. The inverted index for this search index of 2 documents would look something like this. The vertical lines are the postings lists. These are the lists corresponding to the term. So for example, and the horizontal lines are the documents. So there are 2 documents labeled 1 and 2. The posting list Sriram has 2 hits. Those green circles are called hits. It hits on document 1 and document 2. Flipkart hits on 1 and any scale hits on 2. So in this very, very simple search index, if somebody searches for Sriram, you will get documents 1 and 2 as matches. If you search for Flipkart, you'll get document 1 as a match. Now you can form more complex queries. You can take a query that looks like Sriram and Flipkart. Then what happens is the search engine traverses the 2 lists, Sriram and Flipkart, in parallel and finds all the documents that have hits for both of those lists. In this case, it'll be document 1. So this is essentially how it works, but at a very small scale. In a real search engine, you'll typically have millions, maybe billions, maybe even trillions of these documents, and similarly millions, billions of these postings lists. So it's pretty vast, and what Lucene and other search engine technologies do is make these indices really, really efficient in both space and in performance. Now, along with the inverted index, you have the forward index, as I mentioned. So every document has a blob of metadata associated with it, which has information about that document, maybe the entire text of the document, maybe some parts of it. But the idea is that this forward index contains all the information you need to perform the ranking that you need to figure out how good that is a match for the query. It might have other information also in the forward index, such as what you might need to display the document to the user from the UX. Now, when I started, I said you enter some text in the search box, you hit enter, and then those words are then searched in the index, and then the matching documents are returned. If you did just that, in fact, many search engines, even today, some of the more primitive search engines today, actually only do just that. You'll see it as you used it. I'm sure you will notice that. That is not the greatest of experiences. So you want to do some additional processing before you actually send the query to the search engine. So that process is called query understanding. Some very simple functionality that query understanding would cover are things like spell correction. Or if you have plural, you might want to remove the last S so that you match not only all documents that have different forms of that word, and so on. Right? So for example, and then you might also have synonyms. So, let's say you're searching on Flipkart, you want to buy chappals. We might actually use query understanding to say slipper is a synonym of chappal. And in addition to searching for chappal, you might also search for slipper. And without that rewrite or without that synonym addition to the query, you might not find everything that makes sense for that query that you typed. You typed it in one form, but there are many different ways in which it could match. The dual of that is document understanding. Document understanding can also do very similar things. It can also take the terms that it has in the document and expand on them. Similarly, if you have a document that is a slipper that is for sale, you might, during the indexing step, add the word chappal as part of that document. Now, you might be more nuanced in this case and during document understanding. If it's a high-end slipper, you may not add chappal as a synonym. Certain slippers might have chappal, certain others don't. So it becomes a choice of you as a search engine engineer to decide what to do in query understanding, what to do in document understanding. Furthermore, document understanding can also do other things, such as figure out how good the document is. What kind of document is it a really high quality document that should be presented more often than not, or is it a spammy document that we should throw away? Things of that kind. So you can do a lot more in document understanding. But the point I want to mention here is that the out-of-the-box systems like Elasticsearch, Lucene, based on Lucene, do not provide too much of query understanding and document understanding capabilities. They do provide some library functions to help you do this, But in general, you're on your own, and you have to add to the search engines to get such functionality working. And then there is the other aspect, which is how do you actually build the index? Now that you've done this document understanding, that you have the content to put into the index, again, these systems do provide you APIs through which you can actually build the index. The index building roughly comes in two different forms. One is building the index in bulk. You have all the data for your entire index available. You take all that data and put it together into the index in one shot. The other approach is you want to do it incrementally. Probably you're getting updates to your documents all the time, and every time you get an update, you want to go and incrementally modify the index to keep up to date with what has been changing in the real world. Both of these are valuable. Usually systems like Elasticsearch only support incremental index builds. They don't really support the bulk index building really well. You can do it, but it's difficult to do it with those systems. Lucene does allow you to do bulk index builds. Again, it is not perfect, but you can do it. Bulk index builds are useful, for example, when you get input as you get a dump of input. Say one of your vendors sends you a dump of data about the products that they're selling, in which case you want to take all of that and build an index out of it very quickly. In Uber, we had maps. The maps that we showed our customers in Uber would be from map providers who will provide us map data as in big dumps. I was at Uber before any scale. And then when you get this big dump of map data, you have to very quickly build an index. A bulk index build approach work better in that case. So let me go to, fast forward to about, little over 10 years ago, 2010, type ahead autocomplete. So this was first launched by Facebook in 2010. This is interesting in the sense that there was a time when search was all about typing a query and hitting an enter key and then seeing the results. Type ahead autocomplete was as you type, you get results. And that was a very new concept. And to some extent, for a period of time, also to some extent, not understood as very useful. But right now, all of you know that this is a pretty standard thing. It is expected in most search engines. So how does type ahead and autocomplete work? So the first thing I wanted to mention is Facebook was the company that launched it first in April 2010. It was a few months before I joined Facebook. And it was a big thing over there. And it was first built in a very, very custom manner. The data structures used were not scalable. It couldn't be, you couldn't run experiments on it and so on and so forth, but it worked. So it was sort of the very first version. But as type ahead and autocomplete evolved, there were generally two strategies that have been used for building it. One is using tries. So you build a try of all your words, and then you walk the try as the user types. The other, which I prefer more, is term prefixes as postings. So take all your terms and build postings just like you build postings for any other word in your index, but build those postings for each of the prefixes. I prefer the second approach just because the infrastructure you use is the same. You can continue to use Lucene to index your prefixes. Everything that Lucene supports, such as building indices, incrementally building, modifying the index, scaling it, restarting, all the productionization of all of that is you get for free. You don't have to do all of that once again for a try system, right? So I prefer using the term prefixes. And then what does type ahead return? You can either return query suggestions, which is what Google does nowadays. In fact, most companies or most search engines just do that. As you type, you get query suggestions. Some search engines also give you full search results. So you as you type, you get results matching that prefix that you typed so far. The other big thing that also happened roughly around the same time, 2010, 2011, is personalization. Until then, personalization did exist, but it was a very tiny amount of personalization. You do the full search, and at the very last step of the search process, some minor personalization would be done, but not a lot. personalization as a fundamental aspect of search, again, happened roughly around 2010, 2011. And the idea is that you use information beyond the actual text of the query that the user has typed. And it could be customer taste, recent history, recent activity of the user, where the user is, the location, time of day, and so on and so forth. Simple examples like in Uber Eats search. If you search in the morning, you don't get dinner results, you get breakfast results. And when you search in the evening, you don't get breakfast results, right? So simple examples of that kind. If you tend to like t-shirts, when you search for shirts, you probably show more t-shirts than formal shirts, right? So those are all aspects of a customer's personal taste that may not show up in a query that, say, the query might just be shirt, but it's a different thing for different people. So you need to take additional signals about who is searching and incorporate that into the query in some manner. So that's all. That's what personalization is all about. You need to do it right from the very beginning, add it to the query, consider it during retrieval, consider it during ranking, and so on and so forth. So personalization becomes much more important for recommendations, because recommendation engine is really a search engine, but you don't have a query. The searcher has not entered a query. They're just waiting for something to show up in front of them. So personalization becomes very important because you need to have something. You need to have some basis on which to show results to the searcher or to the customer. So let's look at recommendation systems. So the first question that one would ask when you build a recommendation system is it like a search with an empty query? So let's pretend you're in a search engine and you have the search box in front of you and you're about to start typing. So let's say you put your focus, you put your mouse, click your mouse into the search bar and add focus to it. And you're about to type your first character. Suppose you have a list of results that you can see at that point. Is that a recommendation? Or is a recommendation a totally different thing? So again, let's say you type one character in your search engine, you get a bunch of results, right? So is that really close to a recommendation system or no? And the answer to this question is it really depends on the product. So if you look at products such as LinkedIn newsfeed or Facebook newsfeed, they're not queryless searches. They're a totally different beast. They do very different things. They look at things that you have not seen before. It's all about recency, and it does ranking, it does organization of the data in a very different way. On the other hand, if you go to some system like, for example, Uber Eats that I've worked on, a recommendation is more like a search with an empty query. In fact, in the list of recommendations that we provide, we show you restaurants that that you've ordered from before, because we think it's important for you. We're not trying to show you something new like newsfeed shows you. We are showing you something that we think you'll engage with, that we think is important for you, but you haven't yet told us anything more. You haven't entered a search query, so we give you some default behavior, which is personalized, but it's very similar to search. But regardless of which of these two approaches the product takes for recommendations, the personalization still is very, very important, because that's the only signal you have to decide what to show. Finally, I'm going to wrap up the first part by talking about two concepts: pointwise ranking and listwise ranking. So again, most search engines, what they do is they simply assign a score to each document that matches, and then they sort those documents by their score and then return the top scoring documents, and you're done. Listwise ranking is you want to make the entire list more meaningful. So suppose, again, going back to the shirt example, I go to Flipkart and search for a shirt. And let's say I'm a t-shirt kind of person. It's not usually reasonable to have all the top results, or the entire search results page be full of t-shirts, maybe of the same kind and same color, because maybe that's what I like. You might want to have some diversity. You might want to insert some formal wear in there. You might want to insert some collared t-shirts in there, or whatever it is. But you don't want to just blindly show the results that have the highest scores. You want to do some mixing and show some diversity. So that's what listwise is all about. So you want to score the list rather than each individual document. And that becomes important in search. Many people don't do it, but you need to think about that as a fundamental aspect of your stack And you can improve the quality of your search engine quite a bit if you do that. Shifting gears, ML, right? ML-based ranking is relatively new compared to everything else I've talked about so far. It's about 10 years old, I would say. But compared to type ahead and all these other concepts that I've already talked about, which are more like 11, 12, or 20 years old, this is relatively new. But I think most of you have experienced search engines with ML. Many of you have probably worked on ML systems. And it's gaining popularity, and I don't think there's any end to it. ML is gaining grounds very massively, not just in search, but in all other disciplines. And it's the need for MLs is and the need for high performing infrastructure, distributed infrastructure for ML is also going up and up. There doesn't seem to be any end to it. In search, we've been using it probably for the past 10 years. It finds its use mostly in the final ranking step, the very last step of the ranking that you do before you show the results to the user is when ML has maximum value. And that's because that's where you get the most feedback for the ML algorithm that you can use for subsequent training for the next version. So that's where ML has been found most useful. The earlier steps are usually more heuristic based, where you try to take a large number of results and filter it down to a smaller set and then apply ML on that smaller set. Unfortunately, it is overused. And I think care should be taken not to do that. If you think about it, it is now the coolest thing to do. So everybody wants to come and do the work on the ranking step of a search engine. And what I've seen more recently is too much focus is placed on the ranking step, and all other steps prior to that get defocused, unfortunately. And you should try to avoid that. So very simply, don't do something in the last step of the ranking stage with ML if you could have done it in an earlier stage. So as a simple guideline, just do that. So for example, if you search for shirt, then you filter out all the documents that don't have shirts, that are clearly not shirts in the filtering step. Don't wait for the ranking step to filter it out for you or score it low for you. And I'll spend a little bit of time on objective functions, features, and training data. These are the three primary things that you look at when you do ML for ranking. You want to know an objective function that you want to maximize for your scoring, and you probably do that in collaboration with your product managers, with your business. It might be you want the customers to buy buy as much as possible, or you might want to have your customers' ability to buy as quick as possible. You might want them to spend more time on your website, whatever it is, right? There are many different objective functions that may mean more for your business. You choose what that objective function is. And then once you have that, then you come up with features that your ML system will take advantage of to determine what the best results are for a query. And then you need to provide training data to train that algorithm on those, to use those features in the right way, right? So the first thing I would say is only use meaningful features. That this is my personal opinion. There are many data scientists who would tell you, let's just throw all the features that we can think of, anything that can translate to a number about a document or a query. Let's just throw it into the mix and let the ML system figure out whether that feature is useful or not. The main problem with doing that is you get a lot of noise, and you need a lot more training data to help the ML system figure out whether that feature is useful or not. At the end of the day, my own personal opinion is that it comes in the way, it wastes time, it ends up building a system where the ranking is not as good. The other aspect is, for the training data that you pick, you need to figure out what is the training data a positive sample or a negative sample, and if so, what magnitude of positive negative is it? You want to give it some weightage. You want to figure out whether it's positive or negative. Let's start. I'll do this with an example. Suppose you have a search engine that shows 7 results, and the user engages with the third result. then I think it's very clear to everybody that that third result must be given a positive label, right? And with some weight. One might argue that given that it's the third result, its weight should be more than if the first result was clicked, because the user spends some time going down the list to the third result. So maybe the third result being clicked means the third result is really important. So give it a positive weight. How should we assign negative weights for results? What are the bad results in the search list? There are different people who do different things, and I've seen people giving all the remaining results a negative score, and that is wrong in my opinion. That is generally considered wrong. Usually, you assume people look at the search results from top to bottom. So maybe they looked at R1 and R2, they didn't like it, and they went to R3 and they liked it, and so they engaged with it. So you give usually you give the first two results a negative label and the third result a positive label, and that works very well. You might want to give R1 a much higher negative weight than R2 because that was at the top. But those are nuances that you can play around with and figure out as you iterate on your systems. But it's important to come up with negative and positive labels that are realistic, that sort of mirror what your user would have perceived about the results, not some arbitrary labeling that you just find quick and easy to do and very quick and dirty in some sense. And finally, you should try to figure out in your features and training data and also your strategy for ranking, how you can incorporate list-wise ranking. So there's a whole area called learning to rank, which covers this topic. I'll go into a few other side topics. One is knowledge graph for your documents. This is something that you do ahead of time before you build the index. What you want to do is you want to represent your data in a manner that enriches, that gives you an enriched view of your data. So if you take your Flipkart product catalog, your product catalog is not just a list of products and their prices and maybe their characteristics, but there might be relationships. Maybe somebody who buys a pair of shoes might also want a pair of socks. Maybe if somebody buys a pair of shoes, they might want to buy shoe polish. Maybe you know how long the shoe takes to wear out, and so you want to know when to recommend that they buy their next pair of shoes. So there's a lot of other information that goes with that thing rather than just the product and its product metadata. And you want to figure all that out. So the first thing in this whole process is to be able to represent your data in an effective manner. So have a durable representation of your entities, where you store the entities, the metadata of the entities, and also relationship of those entities with other entities. So shoe is a footwear, it is like a slipper, it goes with socks, so on and so forth, right? And and the way you do this is usually through some fancy ML algorithms. You perform lots of offline inferences, and you can do this very easily because you're not time constrained. You can run a large job that runs overnight or whatever across all your entire corpus and really extract lots of rich information about it that you can decorate your graph with. Then this becomes a source of truth for your search index. Now, once you've built this graph, use that to build your search index. So in addition to just the terms that you can pick from the metadata, you can also encode your relationships, the edges, into the index. You can then use that to do richer retrieval, richer ranking, and also other subsequent recommendations. In some sense, this is document understanding on steroids. Another topic is embeddings. Embeddings are essentially a vector of numbers that characterize an entity. Entities can be documents, customers, or even individual queries. So maybe me as Sriram might have let's say 128 size vector with numbers in it that represents everything about me. So each of us may have 128 sized vector. And by looking at that, you can probably infer a lot about each of us. Usually these vectors are generated by machine learned algorithms such as matrix factorization. Humans really can't make any sense of what each individual component of the vector means, but the system that you build around it can do actually pretty cool things. What you can do is you can take two entities, take the two vectors, and do a dot product of those two vectors. That is, do a product of the corresponding elements of the vector and then sum it up. And that number is a very good representation of the closeness of those two entities to each other. So, for example, I might want to search an index for all the documents for which the embeddings between me and those documents are the best. So that's what embedding-based retrieval is. Retrieve the documents, as I mentioned, that have the best embedding for me. Now, if you think about this a bit, you suddenly realize that your inverted index-based index, like Lucene, how can it do this? And this is what people have started worrying about. And so what happens is, and by the way, after you do the embeddings, you still need to do those additional ranking steps. So this has shown to be pretty valuable, and it's a cool new way of doing things. And given that systems like Lucene and similar systems like that, inverted index systems, don't seem to be able to provide this functionality, other systems have been built, and some examples are Phase from Facebook or Milvus, which is an open source system, and they only do this similarity-based retrieval using embeddings. So this is a cool new thing that is happening. It is more important for recommendations because, again, recommendations don't have a search query, and you use the embeddings of the searcher and the embeddings of the document to find the best matches that you do, and then you send that to the ranker. I personally, again, feel that having just an inverted index-based approach or an embeddings-based approach is going to two extremes. I would like to see the two approaches combined. At Uber, we actually built a retrieval operator in the inverted index to support embeddings. We also did it at Facebook when I was there before. It so happens that an inverted index-based system can do a pretty good job of retrieving Boolean embeddings. Boolean embeddings are embeddings where the values such as 0 or 1 as opposed to any number. And we have shown that if you take, say, for example, an embedding which is of size, say, 64 numbers, that's typically a small embedding. A different embedding of, say, 128 numbers, which are Boolean, might provide you the same richness of information. You don't lose too much. So using 128 sized Boolean vector can work almost as well as a 64 sized integer vector, but this 128 sized vector can be retrieved with an inverted index system. So if you can do that, the nice thing is that you can combine the two. So for example, you might want to retrieve all documents that have the word slippers in it, but amongst those documents, you want to retrieve the documents that assist you by embedding scope. So we can do all these things by combining these systems. So it is possible to do. We have done it. We have built it, and it does run well in production, and it shows its value. So this is one of the more recent things that we have worked on. So getting almost to the end of my presentation, putting everything together, right? So I've talked to you about many different components, ingestion and all the way to ranking. How do you put these things together? Now, this is itself a complex problem. And in my opinion, not too many systems have really done a good job of putting all these things together. So Elasticsearch puts together the retrieval part. There are ranking systems like Michelangelo at Uber that put together the ranking part. And usually search engines are built in this manner. You probably have seen some of these also in your companies. You have a front end that first goes to a retrieval system, gets all the matches for your query, and then goes to a ranking system to rank those documents, and then returns the best results. This approach is costly, very painful, and it takes a long time to do this. So what I think is we need better ways, better abstractions to take all of these systems and put them together in a more efficient manner. One of the things that I'm looking for at any scale, which provides higher level abstractions for distributed systems, and it has already succeeded very well in doing this for ML systems, pure ML systems. I feel like we can combine that capability to include ML plus non-ML systems. And one of the things I'm looking forward to in the next year or so is probably to put all of these systems on top of something like Ray and providing a good integration that somebody can take out of the box without worrying worrying about combining everything together manually in some hacky way. And I'm done. This is my last slide. I wanted to share some parting thoughts. I don't have too much time to cover everything in detail. The first thing I want to say is search is an approximate system. The search results that you get are not necessarily measurable by a unit test, right? You can't say this is exactly what results you need. And when you have this kind of stuff, you can actually make your distributed system better, more efficient. Elasticsearch unfortunately has gone to extents to become exact, and it becomes a little more unwieldy because of that. So when you build systems, keep this in mind. People are not expecting that a certain result in your search results. And if a machine dies, you don't have to worry too much about getting the results from that machine for that particular query. And take advantage of the fact that search is an approximate function. If you build ML systems, try to have a baseline that maybe has been built with intuition, because many times you might see that your very first version of your ML system might not beat your intuition-based system. And you might just keep iterating and think you're doing a great job, but if you had built a system without ML, you might have built it better in the first place. So have a baseline that you challenge your ML systems with as a starting point. And finally, customize your strategy to your problem. Don't take a solution that, say, Google has solved for a search engine and then try to use that for a much smaller problem in some other company. So there are many different ways to solve the same problem, such as spell correction. Use the right solution for your problem. And I'm done. Sorry, I might have gone over time a bit, but thank you for your time. I hope my presentation was useful for you. If you have any questions out here, I'll be happy to answer. I'll hand it back to the MC to deal with the questions. Thank you so much.